So let's say we're going to let R be the triangular region with the following vertices. This pen seems iffy. Let's see what we got here. Yeah. 0, 4, 3, 0, and 6, 4. It might not be later. I like the way these pens write, but I feel like the ink doesn't always look from acronyms super easily, which is disappointing because they write pretty well. So, and what we're going to do is describe the region using both kinds of cross section. Describe using vertical and horizontal. And so definitely, if you're describing a region this way, it makes sense. You usually want to draw a picture of it. And this shouldn't be too bad, right? It's just a triangle. Let's see, I've got the points 0, 4, 3, 0, and 6, 4. And so it's looking like this. So there's my triangle. And let's go ahead and do horizontal cross sections first, even though the problem in your assignment says vertical first. So using horizontal cross sections, I'm going to draw a little horizontal strip. Again, not necessary to draw the strip, but it reminds me of what I'm doing. So let's draw this horizontal strip. And so when I do that, I know that my inner limits of integration for my double integral, right? So basically, we're going to do a double integral, and the inner limits are going to be x as some function of y to x as some function of y. The lower limit is the left boundary. The upper limit is the right boundary. And then the y values are just how low we go and how high we go. That'll be a dx, that'll be a dy. So that's, let me click on that, sorry. The camera can go away. Okay, so that's very generally what we've got. So really, all we really have to do here is figure out how to write this line and this line as functions of y, I guess. I'm still going to do it like a function of x because that's how I know how to find the equation of a line. So for this first line here, I know that my slope is negative, right? Because I'm going from this point to this point, and I can read it off pretty easily. I'm going over 3 and down 4. So my slope is going to be -4/3. You could also use the slope formula and do 0 minus, let's see, yeah, no, 4 minus 0 over 0 minus 3. That would totally work as well. And so the equation here, since I have the y-intercept, the equation of this line is going to be y equal to -4/3 x plus 4. Or solving for x, because I want x as a function of y, I'm going to multiply everything by -3/4. Let's see, 4 times -3/4 is -3. And then add 3 to both sides so that x is equal to -3/4 y plus 3. That's my right boundary, or my left boundary, my lower x boundary. So my lower boundary is going to be -3/4 y plus 3. And then to find the upper boundary, we're going to do the same sort of thing. Now, just like the problem you have on your homework, this problem is a triangle that's isosceles, right? Both sides are kind of going over and up the same amount. You can also still look at the points and say, okay, from here to there, I'm going over 3 and up 4. So my slope is going to be +4/3. And then doing it the same sort of way, I would do y. So actually not quite the same way. I'm going to use the point slope form. and say y minus the y coordinate equals my slope times x minus the x coordinate. I would, well, I know I'm going to need y as a function of x. Let's go ahead and multiply that and say y equals 4/3 x, and then 4/3 times minus 3 is minus 4. And then we could also solve for x as a function of y. We can multiply everything by 3/4. 3/4 y equals x minus 3/4 of 4 is 3. And then x equals 3/4 y plus 3. So that's going to be my upper bound. Positive 3/4 y plus 3. And then the y limits are really, really not terrible to look at. If you look at that region, how low does that red strip go? How high can it go? Right, that's it. Right, the lowest y value of that region is 0. The highest y value of that region is 4. We're done. And that's all this question is asking for. This is how we are describing the region using horizontal cross sections. It's not asking us to evaluate this integral or anything, right? Because if you evaluate that integral, you would just get the area of the triangle, which we could find in a less complicated way. Anything else to say about this? No, I think that's kind of it. That's how now you might use words, but I feel like this is what the intent of this problem is, to describe it using a double integral. And then we can do the same thing for vertical, or I should say a similar thing for vertical. Except now we switch it up, right? Now the, yeah, that's the reason I was doing the vertical second. Because the vertical requires a little extra. Because if you draw a vertical strip, well, depending on where you draw it, you have a different bottom function. So we're going to have to break it up into 2 integrals to do it using vertical cross sections. So the first integral, I should say the first double integral. So let's do this one. So we're going to do from x going from 0 to 3 to do this left half of the triangle. And then y is going to go from a bottom function of this line here, which we know is y equal to negative 4/3 x plus 4, to the top function, which is just y equal to 4. 1 dy dx. Now, I don't think it's what they want, but one way you could just describe it right now is just double it. I don't think that's really what they're going for, though. That feels like it would be really not in the spirit of the question. So we should then add on the area of this right-hand half, which is going to be x going from 3 to 6, y going from this function, which is 4/3 x minus 4, to the upper function, which is still a 4. 1 dy dx. So something to be aware of, sorry, for a question like this. I've seen people be kind of tricky with questions like this in the past. Someone might give a question like this on the test and say, describe the following region using an integral, emphasizing the singularity of the integral, meaning that if someone wrote that, you would have to do it using horizontal cross sections, because you can't write that region as a double integral, as one single double integral using vertical cross sections. I don't think that Dr. Dahl is tricky like that, but I've seen it in the past, so I wanted to mention it. But that's how we would do something like this. So now let's extend this to, it's not quite the same as what I want for question 3. Same idea though, yeah, sure. So let's say we have, I was going to use rainfall. So let's say we have the following. Now, the amount of rainfall per year in the triangular region described above. That could be, I might have to pick nicer functions. Sure. Above is given by the following. It's given by f of xy equal to, I'm just trying to make sure I don't pick something that's really challenging to do. Sure, yeah, that should be fine. Let's say it's going to be, okay, I'm just making things up. 25 minus x squared minus y squared. Let me make that a little bit bigger. Let's make that 100, not 25. Why might I care? Because I want numbers to be positive. Let's say that's inches. So if we know what x and y are, we know how much rainfall we got in a given year at a particular point in inches. So if x was 1 and y was 1, we're getting 98 over 10. We're getting 9.8 inches of rainfall at that particular point. Okay. So what we're going to first calculate is the total rainfall. How much total rainfall is there? Over the entire region. So the nice thing about this is if you've already done the first part of the problem, the second part's really easy. So the first part of the problem calculates the area of the region. Either way you want. I'm probably going to use this first one because it looks like it's going to be easier to deal with. And things are probably going to be messy. That's all right. The second part of the problem is just to calculate the total rainfall. So we're just going to do the total rainfall. That's going to be the double integral. Same limits of integration, but now of this function. So it's going to be, and things are not going to be pretty here. I might abandon ship for this particular one because it's kind of gross. Let's take a look. We're integrating this. So we're integrating 100 minus x squared minus y squared over 10. Oh, sorry. So, yeah, maybe should have picked a slightly easier function, such as life. So we can do this, right? The calculation is not particularly nice, but we can so totally anti-differentiate this. I would probably bring out the 1/10 and write it as 1/10 integral from 0 to 4. And then I'm going to start anti-differentiating the 100 minus x squared minus y squared with respect to x. So I'm going to get 100x minus x cubed over 3 minus xy squared, evaluated between, yeah, good times. dy. And then we have to plug that in, and that's where things are going to get a little bit messy, especially with the x cubed there. But we can do it. So we're going to get 1/10 integral from 0 to 4. 100 times 3/4 y plus 3 minus 3/4 y plus 3 cubed over 3 minus 3/4 y plus 3 times y squared, and then minus all that stuff as well. So minus 100 times negative 3/4 y plus 3, and then minus negative 3/4 y plus 3 cubed over 3 minus negative 3/4 y plus 3 times y squared. Clearly not very nice. I probably don't think it's in your best interest for me to keep doing this particular problem. So let's pretend like I should point out, one could totally multiply this out and get the total rainfall, right? You could multiply this out, you could anti-differentiate it, you could plug in the limits of integration, and you could get something gross. It'd be fine. So let's pretend we did this and we got some number. I'm going to make up something ridiculous. Let's say we got 1,296.5. I doubt that there's no way that's the right number. I'm just pretending. We are pretending. Okay. So what that's telling me is that there is that many inches of rainfall total over the whole region. So now what we're going to do to find the average rainfall is we're going to take all that rainfall over the entire region and divide it by the area. So that we get the rainfall per square, whatever unit of area we have. So if our region, if this were measured in miles, like this was 4 miles, and this was 6 miles, then this total region, well, we can even calculate. So you could calculate this area the hard way, or you could do this double integral and get the area. Or not, right? That's a triangle. The base is 6, the height is 4. The area is 1/2 times 6 times 4, which is 12. So the area of my triangle, the area of my region, is 12 square miles, if you care about the units. And then the average rainfall, or more generally, the average value of the function, is going to equal your total rainfall divided by the area of the region, which in this case, pretending like my number was real, would be 1,296.5 inches of rain divided by 12 square miles. And your units would be inches per mile square, or inches per square mile. So the whole point of this is that if you're trying to find the average value of something, whether it's the average height or the average density or the average whatever, you're just taking the integral over the area, over the region, and then dividing by the area of the region. That's what, and just like in, I hope you saw in 17B when you learned how to calculate the average value or the average height of a function. So maybe I should say that just to make sure everyone's on that page. So we have a 2-dimensional and a 3-dimensional kind of analog. So in 2 dimensions, this is my function, and we're going from, say, like A to B. I want to find the average value. Well, the average value is going to equal the total divided by the length. It's going to equal the area divided by the length, which in this case is going to be, well, the integral is the area under the curve. And the length is just B minus A. Once upon a time, a student of mine explained it to me this way. I think it made a lot of sense. And some of you already heard this because you saw me earlier today. So I used to say this, imagine you have an ant farm, but now I have to ask, do you know what an ant farm is? Ant farm, ever heard of one? Okay. So I actually had an ant farm when I was a kid, had little lime green borders, and you put like the rocks in it and stuff, and it looks kind of like this, right? And then we're gonna not put ants in it because what we're about to do could kill them. But if there were ants in it, right, they make little tunnels and stuff. But the point is, in the ant farm, in your ant farm, the amount of rock or sand or whatever you're putting in there isn't going to change, right? I put it in there, I close it up, we're done. Now we're going to shake it up. We're going to shake it up until the rocks are level. Apply shaking. Okay, great. The amount of rock didn't change. So this area here, the area or the amount of rock is the same as it is here. This height, well, it's all the same height now. That exactly is the average height of the function. But we can see that the average height, well, we know that the base didn't change and the area didn't change. So since the base times the average height has to equal the area, then the average height must be what we said it was. It's got to be the area divided by the base. Or more generally, the integral from a to b of f of x divided by b minus a. And that idea can be extended to a third dimension. Instead of your function being two-dimensional like this, you can say, well, okay, same idea in 3D. We're going to take now, this is where my drawing skills might be a little less than excellent. But we're going to say, like, we have some surface. We'll try and draw it so it's not terrible. Sure, there's a surface in 3D. You can kind of believe that we got something like that. And I'm drawing it very much so that, like, these points are over the axes. And so we can say, okay, the average value of that function, it's the same idea. The average value of this function of two variables is going to be exactly the volume under the surface, or more generally, just the double integral of the thing. Because maybe you're not actually calculating volume. Maybe you're calculating mass, or maybe you're calculating total rainfall. But whatever you're doing is to calculate the total amount, you're doing the double integral over your region and then dividing by the area of the region. So the average value here is just going to be the double integral from, I really should just write double integral over your region of your function, whichever way it works, dx dy or dy dx. We write dA when we don't know, when we're not specifying. And then we're going to divide that by the area of the region. Which, if you wanted to, you could say that the area of the region, if it's not just something nice like a rectangle like this, which is not always going to be a rectangle, so this is going to be something you actually have to work at. But the area of the region is just the double integral of the region, sorry, over the region of 1, right? Just like we've been calculating areas before. So that's how you calculate the average value of something that's a function of two variables. And oh yeah, this part here in the XY plane, right, that is our region R. Okay. I do think, yeah, sure. So I guess I should say questions about anything I've said so far. Go back, revisit something. Okay. So average value is not that bad in that you're just really calculating either the integral or the double integral and then dividing by either the length or the area of the region. I will point out that in problem 4, there's parts B and C where you're finding the average width of the plate and the average height of the plate. So just kind of to focus on that for 1 second, meaning a couple minutes. Let's say we have this region. So the region bounded by, let's just make something up that's super fun. Y equal to x squared and y equal to 2x. And so if you set those equal to each other, x squared equals 2x. X squared minus 2x equals 0. Factor out an x. You get x equal to 2 and x equal to 0. So if I was going to try and write this region using a double integral, I could do it using vertical or horizontal cross sections. So let's draw it. Good drawing. He says to himself. So those are my points. Here's the point 0, 0. Here's the point 2, 4. And if I wanted to find the area of the region, we can do it either using vertical cross sections or horizontal cross sections. Vertical all things being equal, typically we're given y as a function of x, not always, but typically. And so if there's no good reason to do horizontal, typically vertical is the way we go because you're usually given y as a function of x. So if I was trying to find the area of this, I would do it vertically. And I'd say, okay, my inner limits of integration are y equals x squared to y equals 2x. If I hadn't drawn a picture, how would I know which one was bigger? Well, they intersect at those 2 points, but between those 2 points, there are no points of intersection. So between those 2 points, you could test a point to see which function value is larger. So between x equals 0 and x equals 2, I could plug in x equal to 1. If I plug in 1, 1 squared is smaller than 2 times 1. So I know that the function 2x is the larger function. That's one way to check it if you don't draw the picture. And then that's going to be my d. Oh my gosh, why did my brain get dy? And then we're going to have x going from 0 to 2. So that'd be one way we could do the area of the region. Or horizontally, we could do the inner now would be, so we're doing horizontal, we're going lower limit is left hand limit. So it's going to be x equals y over 2. And then my right hand limit is going to be y equals x squared, which is x equal to the positive square root of y, because we're on the side of the y-axis where x is positive. And then y is going to go from a low of 0 to a high of 4. So these are the ways you could describe the region. And then the way you would calculate the average height of the region would be the area divided by the length. So in this case, it would be either one of these double, I suppose we could calculate one of these double integrals. I really was trying to like be lazy and avoid doing the work, but let's do it real quick. And I'm going to calculate this one because that just feels more natural to me. So calculating that, we've got the integral from 0 to 2, the integral from x squared to 2x of 1 dy dx. So here's the thing, and you should probably, I bet you already know what I'm about to say. If you're integrating 1, you're going to get the variable y in this case, and then you're going to plug in your limits of integration. So I feel like you should be able to jump straight from here to, oh yeah, we're doing the integral from 0 to 2 of 2x minus y squared. Sorry, x squared, apologies. I don't think that's a huge leap. To be like, oh yeah, we're getting y, and then we're plugging in 2x minus x squared. And then we're going to anti-differentiate again. We're going to get x squared minus x cubed over 3 from 0 to 2. We're going to get 4 minus 8/3 minus 0, which is going to be 4/3. So that's the area of that region. So then the average height is going to be 4/3 divided by the length, which is 2 minus 0. Right? The length is from here to there, which is going to be 2/3. Whereas the average width is going to be the area divided by the height. So we're going to get still 4/3, but now divided by the height, which is 4. I don't honestly know if I've ever seen someone mention average width before. That's kind of a new concept to me. I feel like I've never heard that one. It's obviously, or maybe not obviously, but it's very analogous to average height. It's just you're doing the other dimension, but it seems a little weird to me. But it should make sense, right? That the what are the words I'm trying to say here? That the actually, right? Yeah. So brain. The length times the average height should give you the area. And the height times the average width should give you the area. But it's interesting that the average height times the average width doesn't give you the area. Kind of weird. Not really weird, just, but it is true. You would kind of think they would, right? Like if you took the average of all the heights and the average of all the widths, you think you get the area, but you don't. Okay, so other things to talk about. there's one other thing specifically that I want to make sure I mention, because there are a couple problems. I thought there weren't any like this, and then I looked at homework and there are. So let's, how much time have I got? Sure, yeah. So let's look at this interval first, which is not the kind of problem I'm actually referring to. But just to kind of remind ourselves of how these double intervals actually work. So just like with partial derivatives, when you differentiate with respect to one variable, you think of the other variable as being constant. The same is true with double integrals. When you anti-differentiate with respect to one variable, you treat the other variable like a constant. So if I'm going to anti-differentiate this, I might even try and make my life maybe a little bit easier to see what's going on by pulling out the things that are constants as far as my inner variable is concerned. So my inner variable is y, which means that every factor that doesn't have a y in it is acting like a constant. I would probably benefit from rewriting this as pulling out that 2 over x plus 1 in front of the integral from 0 to x. This is a perfectly valid thing to do. As far as this inner integral is concerned, the 2 over x plus 1 is a constant. And constants get to come out of intervals. And then we can anti-differentiate this using our usual rules. That's going to equal, so my outside part is still the same. That 2 over x plus 1 is just hanging out. You could even put the 2 on the outside of this, right? That would be perfectly fine as well. The integral of 1 over y plus 1 is the natural log of the absolute value of y plus 1 from 0 to x. And now we're going to plug in those into integration. We're going to get integral from 0 to 4, 2 over x plus 1 times natural log of x plus 1. And I'm going to drop the absolute value because the natural log of x plus 1, if x is between 0 and 4, then x plus 1 is certainly positive, and I don't need to take the absolute value of it because the absolute value of it is just already positive. It's also okay to leave it. And then minus the natural log of 0 plus 1, which definitely is in our interest to make sure that we observe that that's the natural log of 1, which is 0. So great, now we are doing the integral from 0 to 4. Let's pull out that 2 of the natural log of x plus 1 divided by x plus 1. It's probably time for a U-substitution. What's a good choice for you here? There's actually probably 2 good choices for you here. You could think about making it u equal to x plus 1, but you're really not solving the problem of the natural log there, right? If u is x plus 1, you're just going to get natural log of u over u du, which is still just as complicated as, or almost as complicated as it was before. I think the better choice for a u sub here is letting u equal the natural log of x plus 1, because the derivative of that is 1 over x plus 1 times dx. And then the integral of the natural log of x plus 1 over x plus 1 dx becomes the integral of u du. Notice I'm doing it off to the side because I don't want to worry about changing my limits of integration. So I'm going to do this antiderivative over here. I'm going to get u squared over 2. I'm going to get natural log of x plus 1 quantity squared over 2. And then I'm going to throw that back in as my antiderivative of my integral of my function. So I'm going to get 2 times that antiderivative, natural log of x plus 1 quantity squared over 2 from 0 to 4. 2's cancel. Yay. We plug in 4. We get natural log of 5 quantity squared minus we plug in 0. We get natural log of 1 quantity squared, but that's 0. So our answer is the natural log of 5 quantity squared. Be careful, we can't bring down that 2 here. We have to leave it as a natural log of 5 quantity squared. There is no other simpler way of writing that, unfortunately. Okay, so Yeah. The thing I wanted to mention was, where'd you go? Not you. Not you. Sometimes the double integral you're given can't be done the way it's written. Here's what I mean. Let's say we wanted to calculate this double integral. The integral from y equals 0 to y equals 2. Then the integral from x equals 1/2 y to x equals 1 of e to the x squared dx dy. And it should tell you e to the x squared is famously not antidifferentiable. If you see e to the x squared, you should be like, okay, something's up. I can't, right? If I'm trying to antidifferentiate this with respect to x, I've got a problem. That cannot be done. There are lots of things that can't be antidifferentiated, like sine of x squared or like the square root of 1 plus x cubed. There's lots of things that just don't work. There's no, I think the word specifically, there's no like elementary antiderivative, meaning you can't write the antiderivative as a combination of like regular functions, like sine, cosine, tangent, e to the x, natural log of x, that kind of stuff. You have to like say the integral is the integral, right? That's not a nice answer. If you do it on like a Wolfram integrator or some other integrating thing, they'll be like, the integral is I of x, where I of x as a function is the integral. It's kind of a cop-out, but there are reasons why they do that. So we can't do it this way, but what we can do, what we have to do, is change the order of integration. But to do that, we need to know what the region looks like. That's why we spent time practicing writing the region using vertical and horizontal cross sections. So if we need to go from one to the other, we're capable of doing that. So I need to draw this. So I'm going to draw the inner limits first. So I've got x equals 1, which is a vertical line. And then I've got x equal to 1/2 y, which is a line that goes to the origin. And then it's got a slope of 1/2. So it looks like that. Probably a good idea to figure out where these intersect. That's going to be, well, if x is 1, then y is going to have to be 2. So that's the point 1, 2. And when I'm drawing it this way, right, I'm thinking of this boundary as my left-hand boundary and this boundary as my right-hand boundary. So that's good. It looks reasonable. I've got my horizontal cross sections like that. And then the y values are going as low as y equals 0 and as high as y equals 2. Great. That seems totally like normal for a region. And then I'm going to switch it up. I'm going to reframe it using vertical cross sections. So I've got my region. This is the point, 1, 2. I know that this line is x equals 1, and this line here is x equals 1/2 y. And now I'm going to use a vertical cross section. So I can rewrite this integral as, and it is equal to the thing I'm about to write. Let's see, my inner limits of integration go from as low as y equals 0 to as high as y equals 2x. And then my outer limits of integration are, well, this strip goes as far left as x equal to 0 and as far right as x equal to 1. And my integrand doesn't change, but my dx dy order does change, right? It goes from dx dy to dy dx. And although it might not look a lot different, it's actually very different because now we're going to antidifferentiate first with respect to what variable? I know you know it. Thank you. Yes. So that's a constant. And the antiderivative of a constant is the constant times the variable we're antidifferentiating with respect to. From 0 to 2x. And now we plug in our limits of integration. We get e to the x squared times 2x minus e to the x squared times 0. Or more normally, we have the integral of I'm going to write that as e to the x squared times 2x dx from 0 to 1. And now we can do a u sub. We can let u equal e to the x squared. And your du, oh, that's the wrong, I mean, technically that would work, but I'm making a choice that I probably actually wouldn't. It's not the way I would usually choose. I would probably actually choose just x squared as my u. The reason being, x squared is a good choice, right? The derivative of x squared is 2x. So du is equal to 2x dx. So then this is going to tell me that the integral of e to the x squared times 2x dx is equal to the integral of e to the u du, which is e to the u, which is e to the x squared. So then this is going to end up equaling e to the x squared from 0 to 1, which is e to the 1 minus e to the 0, which is just e minus 1. So sometimes you're going to have to change the order of integration. And I'll point out, just in case, so, you know, on your homework assignment, that's definitely a problem. On the second part B, it's definitely problems 1D and 1E. You will have to change the order of integration to be able to integrate them. 1D is very similar to the problem, like it's the same type of problem we just did. 1E is a little different. Maybe we have time for one more example. Sure. Let's look at this one. Let's say we want to do the integral from 0 to 9, and then from root y to 3 of 1 over the square root of x cubed plus 9. And this one also can't be done as is. We cannot, I don't know any function whose derivative is 1 over the square root of x cubed plus 9. It's not a good u sub, it's not integration by parts, it's kind of, it's really, I don't actually know this for a fact, but I'd be willing to bet a lot of money that that function cannot actually be anti-differentiated. It could be wrong. Maybe there's some bonkers formula for it. But the point is, even then, it'll probably be super hard. Whereas if we change the order of things, it's probably going to be a lot better. So let's figure out what our region looks like. We're going from x equals root y. X equals root y. I'm not good at graphing. I'm going to square both sides. Say, oh, that's y equals x squared. Except it's actually only the right-hand side of it, because if x equals the square root of y, x has to be positive. Right? You can't have a square root of something and get a negative result. So here, there's my x equal to root y. And then that's my left-hand boundary. So my strip should be horizontal in this way. And then my right-hand boundary is going to be the vertical line, x equal to 3. And then my y's, we go as low as y equal to 0, great. And I would be willing to bet that that point of intersection is the highest y value. And if we think about it, oh yeah, that makes sense, because if x is 3, y has to be 9, which is definitely my upper y value. So good. So we're going to redo this using vertical cross sections. We're going to rewrite this as, so now my inner integral, the lower boundary is x equal to 0. The upper boundary is, sorry, whoa, I said the wrong thing. The lower boundary is not x equal to 0. That lower boundary is y equal to 0. It's probably a good idea to write y equal to 0 there. The upper boundary is y equal to x squared. And then our vertical strips go as far left as x equal to 0, as far right as x equal to 3. Our integral, or I should say our integrand, didn't change. It's still 1 over the square root of x cubed plus 9. But now it's dy dx. And then we can integrate that. We're going to get, from 0 to 3. When I anti-differentiate this, That's all just a constant as far as the variable y is concerned. So I would probably just do it like this. I'd say I'm going to get y over the square root of x cubed plus 9. Or you can write 1 over the square root of x equals 9 times y, but it feels like we can simplify that a little bit. From 0 to x squared dx, and then we're going to plug those in for y. So we're going to get the integral from 0 to 3 of x squared over the square root of x cubed plus 9 minus 0 over the square root of x cubed plus 9 is just going to be a minus a 0. And now we're again in a U substitution sort of situation. We can let u equal x cubed plus 9. du is 3x squared dx. 1/3 du equals x squared dx. Normally what I would do is I would do the u sub and I would actually do the integral of that over here. But I want to show you something else you could do instead. So instead of like doing the integral of x squared over the square root of x cubed plus 9 dx, and then getting the, you know, like, what is it going to be? 1/3 du over the square root of u, and then like doing it and plugging it back, whatever. You can do the integral over here as long as you change your limits of integration. Meaning, I can change this to being in terms of u. I'm going to get, and that's actually, this is actually a real plug for actually writing this is y equals 0, this is y equals x squared, this is x equals 0, this is x equals 3. So when I change things to u, well, let's see. Where'd it go? Apologies. My 1/3 du is x squared dx. So the x squared dx becomes 1/3 du. And I'm going to have the square root of u. But now I'm doing my integral in terms of u. So I should also change my limits of integration. So if u equals x cubed plus 9, if x equals 0, u is going to be 0 cubed plus 9. And if x equals 3, u is going to be 3 cubed plus 9, which is 27 plus 9, which is 36. And that's totally valid. And the nice thing about this is you don't have to change back. You don't have to do your integral and then plug back in that u is equal to the x cubed plus 9. You can just do that. I'm going to rewrite this as the integral from 9 to 36 of 1/3 times u to the negative 1/2. Then we're going to anti-differentiate. We're going to get 1/3 times u to the 1/2 divided by 1/2 is going to be 2 u to the 1/2 from 9 to 36. And then we're just going to plug in the 36 and the 9. There's no reason to switch back to x cubed plus 9 for u. So we're going to get 2/3 times 36 to the 1/2 minus 2/3 times 9 to the 1/2. And those are nice numbers. Square root of 36 is just 6. So we get 2/3 times 6 minus 2/3 times 3, which is just going to be 4 minus 2, which is 2. Clearly someone thought about this problem ahead of time to make it turn out so nice. All right, I should stop. It's 2 o'clock.